Hocam, one more minute. Okay. Just okay. So today we are very happy to host Atac Imamoglu hocamız from ETH Zurich. So Atac Hoca got his BS degree from Middle East Technical University, department. Then both his master's degree and PhD, they are from both Stanford University. Atac Hoca is one of the most important physicists working on the field of quantum information and computation, and especially quantum optics. He's very well known. So also he's interested in semiconductor physics and nonlinear optics. So today he's going to give us a talk about his recent study. And Atac Hocam, hoş geldiniz. Welcome to our YouTube channel. And there are a lot of people who are very happy to see you here. Thank you hocam.
Çok teşekkürler Burçin. Benim için de bu konuşmayı vermek bir onur vesilesi. Konuşmayı İngilizce vereceğim zaten. Onu daha önceden sanıyorum anons edilmişti. Fakat konuşma sırasında herhangi bir soru olursa lütfen şey yapın. Burçin'e haber edin chat room'dan. Durup cevaplayayım çünkü yani bütün planladığım slaytları anlatmam şart değil. Yani önemli olan ana mesajı verebilmek. Okay, now so what I'll do now is I will share my screen and start with the talk. Okay, so as Burçin mentioned, I'm going to tell you about a recent interest of mine or recent work in my group, which has to do with optical studies or quantum optical studies of correlated electrons in two-dimensional materials. Okay, so the people that I listed here are my co-workers. The first line include the people who have done the experiment: Yuya Shimazaki, Ido Schwartz, Tomasz Smolensky, as well as our collaborators in theory as well as in materials around the world. So I would like to sort of start out by saying a few things about the two-dimensional materials. So what these are, they're also referred to as van der Waals materials. So they're characterized by strong covalent bonds in the plane and weak van der Waals bonds that connect different planes. So it's a layered materials that we are talking about. There are more than 5,000 of them that are known. And what makes them special is that it is very easy to exfoliate these materials and go down to the limit of a single layer, a monolayer or bilayer. And really, what is also special is that many of their optical, electronic, and magnetic properties remain robust even when we go down to the monolayer level, right? So we were now really talking about electrons, say, living in a truly two-dimensional world. We could suspend these materials such that it is surrounded by vacuum on both sides, and yet they would retain exquisite optical or electronic properties. So, and as I said, I mean, it's a relatively poor man's material because one can get these materials relatively cheaply, and using a Scotch tape, as many of you I'm sure have heard, you have an excellent chance of getting down to this monolayer limit. Now, what makes them interesting physically is the fact that in such materials, particularly when they are embedded in a low dielectric constant dielectric like boron nitride, or when it is suspended, the dielectric screening of interactions can be reduced dramatically as compared to the usual insulating or semiconducting materials. One can actually use gates to control the charge density in these systems, and in this way probe regimes of relatively low charge density where the interactions could dominate over kinetic energy. So this is characterized by the so-called RS parameter, which basically gives us a ratio of the interaction energy, Coulomb interaction energy to the kinetic energy. And basically, as physicists, we are interested in materials where this RS parameter is large. This is the regime when doing theoretical predictions or calculations is difficult, if not impossible. And the experiments are really worthwhile doing in the sense that you could start out with some models or predictions in mind, but basically you're not fully guided, at least by a theoretical model, because of the complexity of the problem. So what is also interesting is that the monolayer of materials is only a starting point, because we can actually combine, once we go down to the monolayer level, we can combine materials and stack them on top of each other to create heterostructures with very different properties. And we can combine, for example, a semiconductor with the superconductor, just place them on top of each other, or a ferromagnetic material. And in this way, obtain hybrid systems where new physics can be observed. And one example for this, at least in terms of a prediction, is, for example, the P-wave induced superconductivity in semiconductors due to the proximity effect. So people have been pursuing this in standard 3-5 semiconductors, but there the distances, the finite thickness of the system, as far as I know, remains a problem. So another very interesting aspect, which was discovered essentially 2 years ago by Pablo Jarillo Herrero, is the fact that it's not just bringing together two monolayers, but really that changes the physics, but also the angle that one uses to bring the monolayers together. That is, if you rotate one monolayer with respect to the other, then you can get really new properties. Okay, so, and I will give you a brief example of this, but what I would like to sort of mention here is that we're really talking about, in my opinion, a new research field. So we're not doing quantum simulators as has been done in cold atoms in this field. We're designing strongly correlated materials, but these are real materials involving electrons and exhibiting transport properties like superconductivity that can be measured using, let's say, the contacts and looking at the voltage current dependence. So let me sort of give you one example from that really started this field. So on the left-hand side, you see a sketch of two graphene monolayers. So this is the easiest monolayer to obtain, starting from graphite. Right, and the idea is to take two such monolayers, align them crystallographically, and this can be done using second harmonic generation, or as in Pablo's experiments initially, by tier and stack technique. That is, you take a monolayer, you rip it off along a certain axis, and then place it on top of each other. And this way, you know what the crystalline axes are. And if you now introduce a small angle theta when you stack them up, then you see that there is a periodic modulation of the electronic states, and at a much larger lattice constant. So you obtain a superlattice with the lattice constant that can be almost 2 orders of magnitude larger than the inherent graphene lattice constant. So what happens then is that if you look at the band structure, instead of getting this Dirac cones describing the electronic states around the Fermi energy, what you obtain is very different dispersion relation for electrons. And for certain angles, you can obtain flat bands that are well separated from the rest of the conduction bands. And this is, of course, great, because once you have a flat band, then the maximum kinetic energy that the electrons would have to pay, if you will, is given by the width of this band. And if this is smaller than the characteristic energy of interactions, then the system will no longer be explainable using single particle physics. Okay, so this is their by now famous experiment from Pablo's group in 2018. Last I checked, it had about 2,000 citations. And what they do here is that they change the carrier density in a structure that I will show you later, which basically uses top and bottom gates to control using the basically defining a capacitance and controlling the charging density or the electron or hole density in the system. And as they do, they look at the phases of the material through their conductivity measurements, and they see that it can range from a metal to a superconductor, and the superconducting phases at low temperatures is separated by insulating Mott phases. So this created an incredible amount of interest because of its similarity to the strongly correlated materials that have led to high TC superconductivity. The difference here is that the the TC of superconductivity is only a few millikelvin, but it's a much more controllable system, and the superconductivity is obtained at orders of magnitude lower density than one did in the original strongly correlated material systems. And there are a whole wealth of experiments, ferromagnetism, quantum anomalous Hall effect, etc., that have been observed since. And now it's a sort of an ongoing debate to understand the relation between this insulating Mott phase and superconducting phase, the origin of superconductivity. And there was actually a 2-week summer school earlier in July where these ideas or proposals were discussed. Now, what I want to emphasize here is that I will not tell you about graphene physics, but about physics in twisted two-dimensional semiconductors. So graphene is a semi-metal, as I said, that it by itself doesn't have a band gap. But we are interested as an optics group, semiconductors where we can do our spectroscopy, not just using transport, but also optical methods. So you can say an AC transport or AC conductivity measurements. So the outline of my talk is then as follows. So I will first tell you about elementary optical excitations in electron or hole doped transition metal dichalcogenide monolayers. And this is one of the few acronyms that I will use, TMD, instead of saying the whole name of the material. Then I will tell you what exciton polarons are and try to describe to you how we can use them to probe strong electronic correlations in twisted now semiconductor structures. And in the final part, I will tell you about a direct optical signature of charge order in a Mott-Wigner state. That is an optical signature that directly tells us not just that the system has turned an insulator, but also it has a charge order. Okay, so let me start out with some background, assuming that some of you may not know or remember sort of the optical properties of semiconductors. So what I'd like to remind you is a direct bandgap semiconductor like gallium arsenide, which has nice optical materials, and as such, they form the basis of laser diodes that we use pretty extensively these days, and also in communications. So the idea here is this, that you typically consider a neutral system, at least in the introduction, meaning that there is a top valence band, which is all filled with electrons, and then a conduction band, a lowest energy conduction band, which is all free of electrons. Now, if you consider optical transitions in the system, you can at a first glance say that, okay, I will take an electron from the valence band and raise it to the conduction band. The missing electron behaves as a positively charged object, so we call that a hole. And so basically, if you think of it in this way, you will say that there will be a continuum of transitions starting at a band gap and then continuing on for as long as these bands extend. And these transitions are so-called vertical transitions because the photons carry very little momentum as compared to the electrons. So what happens in reality, though, that the dominant feature in absorption spectrum are called excitons. So it's a line, a delta function-like resonance that is below the band gap. And this state or this resonance arises due to the fact that the electron that we excited into the conduction band likes to correlate its motion with the hole that is left behind, because again, the hole is effectively positively charged, electron is negatively charged, they experience Coulomb interactions, and that results in an hydrogenic or positronium-like sort of binding and confined energy states that we describe, the ground state of which we describe as an exciton or a 1s exciton. Okay, so depending on the strength of the screening or the mass of the electrons or the holes, the binding energy of this exciton can range from about 5 milli-electron volts in gallium arsenide, which means that in room temperature you cannot see it, to about 500 milli-electron volts in the materials that I will show you, particularly if they are suspended. So it's basically the material properties determine how strongly tightly confined excitons are. Okay, and one can also, there's even a more extreme limit called Frankel excitons, which are more prominent in molecular systems, where you can really say that an excited electron in a molecule always stays, tries to stay in the same atom, or if it moves such that another electron hops onto the other host atom. Okay, so excitons have large oscillator strength. So, and this we can understand it's in this way. If the electron and hole are tightly bound, then they can easily recombine and emit light. So this, as compared to, for example, a free electron and a hole, they can only recombine and generate a photon if they run into each other, right? So this is no longer an issue in an exciton. Their motion is correlated. And the more closely knit this wave function is, the more strongly sort of bound the electron is to the hole, or vice versa, then the larger the optical oscillator strength. And one last point is that such an exciton, as long as it lives, actually also has a center of mass motion, and this motion is relatively trivial. It has a finite mass, this exciton, that is the sum of the electron and hole masses. And what we need to keep in mind is that if an exciton has center of mass momentum, say k parallel, and if this is a nice two-dimensional material, then when this exciton decays, it generates a propagating photon, but this photon has to have the same momentum as the exciton initially had. And this has to do with the translational invariance in a clean quantum well or monolayer, and which tells us that the momentum along the axis in which we have axes in which we have translation invariance has to be a conserved quantity. And a corollary of this is that if the exciton momentum exceeds omega over c, where omega is the photon energy or the band gap or the exciton energy, then it cannot decay, because such a decay results in a photon that has very high energy and there is no density of states overlapping with the exciton. So excitons can only decay in a so-called light cone. There is only small momentum excitons can decay. Okay, so now this was the story with in the absence of electrons. So what I'm going to tell you is optical excitations, or what I'm interested in is optical excitations in the presence of itinerant electrons or holes, some excess electrons or holes in the system. That means that we look at these transitions when we already have some electrons in the system. So this is the Fermi energy is not here, but rather up there, and we consider how the optical transitions are modified in this scenario. Now, this actually is a rather generic system with a very long history in both pure and applied physics. So many of you might have studied Fermi singularity as one of the sort of simplest to treat many body problems in probably in grad school. So basically, this investigates the screening of an optically generated valence band hole, which is assumed to be extremely heavy. So this is typically done using X-rays, such that the hole is left behind in a sort of a valence band where the electrons hardly hop, and then the electron is excited on top of a Fermi sea of electrons in a metal, and this results in interesting power law singularities in the absorption spectrum, and this has been studied since 1950s or 60s. Now, on the applied side, as I mentioned before, semiconductor lasers or light-emitting diodes, which we have in our houses or everywhere else now for lighting, these are actually devices where light is generated in the presence of electrons and holes, and in particular in semiconductor lasers, these have to be degenerate electrons and holes. Okay, so now, so this is sort of where the field is. Now, I claim that there is a new angle, new opportunity provided by the two-dimensional materials, and that comes from the fact that the optical excitations, as I alluded to, are these very strongly bound excitons. So, which means that the physics is very different from the Fermi singularity in the sense that when we create an exciton in the presence of electrons, the exciton is so strongly bound that it retains its nature as a bosonic excitation, a rigid bosonic excitation that interacts nevertheless with the electrons in the Fermi sea. Okay, so it's now a mobile impurity in a Fermi sea of electrons or holes. Now, what is nice about this system is that it is easy to control the degeneracy of both electrons by applying gate voltages that change the electron density from practically 0 to about 10 to the 13, and also the degeneracy of the excitons, because we can generate them by shining a resonant laser. Okay, so shining a resonant laser will generate a coherent state of excitons, and these degenerate excitons can interact with degenerate electrons, and this is now an example of a Bose-Fermi mixture, a degenerate Bose-Fermi mixture, and this is again a prototypical problem considered, analyzed particularly in ultra cold atoms, and the full phase diagram is not known, but it is expected that that we can obtain rich physics when we explore the whole phase diagram. And the final point that I want to mention here is that these excitons, the impurities that are interacting with the electrons, I will call them dressed excitons or exciton polarons later on, they act as a probe of the electronic correlations. Okay, so how well the excitons get dressed and their properties, energy, oscillator strength, and so on, get modified is actually depending on the electronic state. And if the electrons exhibit correlation effects, this we can read out by looking at the excitons. Okay, so now let me say maybe a few things about the transition metal dichalcogenides. I already told you that these are layer 2D materials. Again, actually, not all TMDs are semiconductors. There are also superconducting ones, metallic ones, or those that exhibit charge density wave order. And ferromagnetic materials are not exactly belong to the same category, but they're also layered materials. Now, the idea is, or the basic structure in TMD is actually what I call a monolayer, is a trilayer structure. So you have a triangular lattice of metal atoms here in dark blue, surrounded by a triangular lattices of chalcogen atoms. So from the column 7. Okay, and those who have nice optical transitions are sort of transition metals, molybdenum and tungsten, and sulfur or selenite as the chalcogen atoms. And most of what I will tell you is on molybdenum diselenide, although the physics is very similar, irrespective of which material we consider. So again, if you consider the band diagram, the free particle band diagram, so it looks a lot like what I've shown you before. There is one difference. So we now have basically a honeycomb structure, effective honeycomb structure, and the interesting physics actually does not take place in the gamma valley, but rather at these high symmetry points, K and K prime or minus K points of the Brillouin zone. Okay, so these are related by time reversal symmetry, and it is at these points of the Brillouin zone that you have a direct band gap sort of transition or nature, and it is here that you find the conduction band minimum and the valence band maximum. So optical transitions are dominated by these points of the Brillouin zone. As soon as you go to a usual bilayer, then the minimum of either the conduction band in tungsten-based materials or the valence band in molybdenum-based materials lead to other parts of points in the Brillouin zone, and the material becomes indirect band gap, and this you will see shortly. So the absorption spectrum, if we just shine light onto this, this is what I was alluding to earlier. So there, this is the band gap, the step-like transition. What you see is sharp peaks underneath, and actually there is a very sharp peak. This is the 1s exciton, where the electron and hole are most strongly correlated with each other. And as I mentioned already, the reduced dielectric screening means that the exciton has this very strong binding energy, ranging from 200 millielectron volts to 500, depending on what material we have around it. Actually, one very interesting property of this material is that this very strong exciton binding, resulting in a very short lifetime, means that even if there is some disorder in the material, the excitons decay so fast that the disorder becomes irrelevant. So those of you are familiar with this concept, there is a quantum Zeno effect that says that disorder scattering is suppressed because of the short lifetime of the exciton. One very nice and interesting consequence of this is that if you take a monolayer suspended in free space, then it acts like an atomically thick mirror, which reflects a very sizable fraction of the incident light. So what we have seen more than 70% reflection, and the highest that has been reported is 85%. So which I find remarkable, that just a single sort of layer of atoms can lead to such a strong optical response. Okay, so now we study these materials using a technique called photoluminescence. This is just to see that the material that we prepared in our sample preparation room is really nice, as we expected. So, and the idea of the experiment is this, that you use a laser that basically takes an electron and excites it into the conduction band, and then this is a high energy laser, and then these electrons and holes relax, as I tried to indicate in these wavy lines, and they, before they recombine, they find the lowest energy state, optically excited state, and that's the exciton, and that results in this peak. Okay, but if you have some electrons in the system, and I'm now considering a very low density, then the motion of the exciton can be correlated with one of the electrons. And what you end up with then is this three-body bound object, which is called a trion. And it's a bound object, meaning that its energy is less than that of the exciton. Its oscillator strength is much smaller, but therefore in absorption, you cannot see this object. But in emission, because it provides the lowest energy state, the carriers relax. Most of the excitons will bind to an electron, and then as they decay, you will see this trion peak in emission. Okay, so that's the story. So the trion is the analog of the H- molecule. So it has a single bound state, and the electrons can be bound to the hole only if they are in a singlet state. Okay, so that's some information that I will come back to later. Okay, so now let's look at charge tunable van der Waals heterostructure. So basically, I will start out with the monolayer TMD, right? So this is our molybdenum diselenide. And what we normally do, and not just we, but the whole community, is to encapsulate this in boron nitride. Okay, so even though suspending it is a lot neater conceptually, this is much easier, much more robust, and it actually results in extremely clean samples. So even better than what you get in a suspended sample. So there are arguments that the transfer of HPN actually cleans away the interface and results in this relatively pure interface between the moly diselenide and any TMD or graphene and the boron nitride layer. So this is a optical micrograph of this device. So it basically, you can see these shadows are indicating monolayers. In this case, this is graphene, and there is a monolayer of moly diselenide here. And there are also thicker samples because basically when we get a large enough monolayer, we do not make sure that it's only a monolayer. So sometimes part of it has several layers, and then it will show up as this darker color. And what is important here is that we also have above and below the boron nitride, we have graphene layers, and we can also contact them and use them as gates. So for us, graphene or multi-layer graphene is basically a gate that allows us to apply voltage and control the charging in this capacitor. You see that what we basically have is a parallel plate capacitor with two sort of gates on the top and below, and the layer that is connected to the ground in between. So what happens now then in this device where we can control the charging density? So we can measure the source drain current. So what we see is that there is a gate voltage region. So in this case, it's only the back gate that is varied, where there is essentially no current flowing through the device. Okay, and at a certain gate voltage, we see that there is an abrupt turn on of the source drain current, and this is the region when we inject electrons into the TMD through the capacitor, and these electrons then contribute to conductivity. If we change the voltage in the other side, even though it's not as neat, and we never in moly diselenide are able to inject electrons in a smooth holes in a smooth way, but you can see that we can inject holes, and they also contribute to a current in the system. Now the question is, what happens to the optical properties? So this is a color-coded plot, which means that if I take a line cut here, I will just see essentially a dispersive line shape, and I can explain why it's dispersive if anyone is interested. But this is in reality this delta function exciton resonance, which changes the reflectivity of when you're on resonance. Okay, and you can see that the reflectance really changes are on the order of unity. So this is the exciton resonance, and what you see is that when there are no electrons, then you just see the exciton. I told you that there's nothing else. But as we inject electrons, this exciton starts blue shifting and losing oscillator strength and broadening, whereas a new resonance appears that is red shifted and that picks up oscillator strength as we inject more electrons or more holes onto the system. So these new resonances are what we refer to as attractive polarons or dressed excitons. And let me try to describe to you what this is and how to understand the spectrum. So this is the only equation that I will show. So just to indicate that basically exciton-electron problem is actually a many-body problem, which we can not solve exactly, but we can try to find approximate eigenstates to the system. So basically, we consider a Fermi sea of electrons, excitons that we can generate, but we assume that the density is very low as compared to electrons in any case. And then there is a density-density interaction between the excitons and electrons, okay? And this interaction constant is actually determined by the Coulomb interaction between in the constituent particles. But if you're only interested in basically low temperatures, low energies, then we can actually replace this by an effective interaction, much like the cold atom community does by replacing van der Waals interaction with the contact interaction. Here we again have defined or described the dynamics using a contact interaction whose strength is determined by the energy of the bound state, the molecule, which is the trion in our case. So trion plays a crucial role, even though we do not see it optically in absorption. It actually determines what the strength of these interactions are. Okay, so this approximate eigenstate, as I said, one can diagonalize the system if one truncates the Hilbert space, saying that the exciton can only scatter one electron hole pair. Which sounds outrageous if you are familiar with Fermi singularity, Fermi-8 singularity, but it works very well because of the mobile nature of excitons. And what it tells us is that the eigenstates of the system are a superposition of a bare exciton and an exciton plus a Fermi C electron hole pair. Or we can think of this, the other part, as a trion excitation, trion Fermi C hole excitation in the system. And but what is really key is the superposition nature, because it is the bare exciton character that gives polarons its oscillator strength. And it is the dressing with electron hole pairs that lowers or changes its energy. Okay, so this we call it a Chevy ansatz after Frederick Chevy, who introduced such an ansatz for cold atoms. But we also learned later on that Robert Souris has basically proposed this in early 2000s. Okay, so now going back to, again, a sample where we inject, control the electron density. You can see that the exciton resonance blue shifts, and we have the attractive polarons. Two things I want to mention here. One is that this attractive polaron resonance can be actually narrower than that of the exciton, which I find remarkable, because you would normally say that if you introduce electrons, there will be dephasing events that will cause line broadening. So this is not true at low densities. The effect of electrons is really only to dress the exciton, or primarily to dress the exciton, such that the line width could actually become narrower. The second and more important thing that I want to mention here is this very steep change of the exciton energy as it becomes the so-called repulsive polaron branch. So this very strong steep slope tells us that we can really, by looking at the energy of the repulsive polaron, which I will call exciton from now on, we can really understand not only the electron density, but also what happens to the electrons and what kind of excitations the electronic system could have. Okay, so now I just want to show you one result of exciton polarons at high magnetic fields. So to basically also comment on this energy level, energy scales. So what you see here is that at 14 Tesla, what used to be this exciton repulsive polaron actually exhibits these very periodic cusp structures. And these cusps are associated with unity filling of the electronic lambda level. So what you can see here, or you can argue that this is the optical Shubnikov-de-Haas effect, showing that the exciton energy as well its line width oscillates periodically, in this case with the density, but of course one could also fix the density and do the experiment with the varying magnetic field. Now, what is not clear, however, is that in gallium arsenide, when you see these peaks, you know that you're dealing with an integer quantum Hall effect, which has been verified over and over again with transport measurements. Here, unfortunately, we could not do transport measurements. And what is, if you look at the energy scales, it's really inverted as compared to gallium arsenide. So the Coulomb energy, characteristic Coulomb energy, basically determined by the length scale given by the magnetic length, is about 24 milli-electron volts. The cyclotron energy, on the other hand, is more than an order of magnitude smaller. So the question is, I mean, can we really talk about a liquid state here, or is it that the Wigner crystal state would win over and basically break translational symmetry spontaneously? So I don't have an answer. So this is an ongoing project in my group, which we carry out using our collaborators from the Harvard group of Eugene Demner. Okay, so now let me sort of take a step back, and I'm running out of time, and tell you about using this repulsive polaron as a spectroscopic tool. Okay, so the starting point is for this is to see if we can determine the charging configuration of the material. So for a monolayer, this is kind of trivial, but what we do is, I think, in terms of seeing the principle, it's important. And this is really, I should sort of give credit to my postdoc Yuya Shimazaki, who invented this method. So basically, the idea is this: that you want to vary the back gate and top gate and get this two-dimensional map. And the map, what you are mapping is the reflectivity at a fixed energy, in this case denoted by this red dashed lines. And what you see is that when there are no electrons, there is a sizable reflectivity. And as soon as you inject electrons, reflectivity drops down dramatically because the resonance is shifted away. And therefore, by measuring the reflectivity at this energy, we can determine if the material is neutral when the reflectivity is large, or when it is n-doped or p-doped. And we cannot differentiate between N and P, but we do so by knowing the expected dependence on the gate voltages. Okay, so in this way, this is kind of a boring sort of charge configuration map, and such structures actually have become famous in mesoscopic physics community for understanding transitions in quantum dot structures in electrically defined quantum dots back in 1990s and 2000s. Okay, and you can see that actually that along this axis, what you are changing is the chemical potential. So even though so the fact that we have two gate voltages, we can change them or in accordance with each other in a way to make sure that we only change the chemical potential without changing the electric field, or we can change the electric field without changing the chemical potential. That would be orthogonal to orthonormal to this one. Okay, so now this is, as I said, it's just to introduce the concept. So let's consider a twisted, in our case, a trilayer structure. So the experiments that I'm going to show you actually involve three layers, two molybdenum diselenide layers separated by a monolayer of boron nitride. Okay, and we introduce a twist to the molybdiselenide, unintentionally, I must admit, but the net result is that I mean, we have very little control over this twist angle, and that results in this sort of periodic modulation or the appearance of a superlattice. Okay, so the structure now looks like this. We have the boron nitride, again, the top and bottom gates, and now we have the two molybdiselenide layers. Okay, so this is how the device looks like in photoluminescence, which, as I said, is used to characterize samples. So this very bright region is when we have this trilayer structure, where this very dark region is when we have bilayer molybdiselenide without HBN, and these less bright regions are monolayer molybdiselenide. And what you see here is then that, as I said earlier, as that if you have a bilayer molybdiselenide, its indirect band gap, it's very dark. Okay, but as soon as you put HBN, the conduction band minima and valence band maxima stay at K and K prime value. So the material is a direct band gap, and this is very nice for optical characterization. And this will then be the region that we are interested in. Okay, so now in this case, we have excitons, but we should keep in mind that there are actually three kinds or even four kinds of excitons. We can have what I will refer to as an intralayer exciton, where electron and hole is in the same layer. So this is what I've been showing you all along. But in this case, and this could be even either in the bottom layer or top layer, okay? But there could also be an interlayer exciton where electron and hole live in different layers, okay? So such excitons actually are normally optically dark because of the vanishing overlap between electron and hole wave function. And their binding energy is also smaller than intralayer exciton because we have introduced this 1 nanometer displacement between the electron and hole. And keep in mind that the Bohr radius of the exciton is on the order of a nanometer. Okay, so now what we wanted to do is to bring these excitonic resonances into the excitonic transitions into resonance, because if we do that, then in the presence of hole or electron tunneling, coherent tunneling, we can hybridize them and form new excitations that are superpositions of an intralayer and interlayer excitons. Okay, and so this is now the again the color-coded reflection map of the spy layer in the neutral region. And what is conveniently the case for us is that because of the different strain in the material, the top layer and bottom layer for most of the material have different energies. So in this spot, the top layer has lower energy. It changes in other parts of the sample. And what is important here is that you see at the two edges that you see lines that disperse, that change very abruptly by changing the top or back gate voltage. So this is a characteristic feature of an interlayer exciton, because if we change the electric field, you see that we are changing the relative energy of the conduction band here with respect to the valence band here. And in this way, we have because of the finite dipole, if you will, of the interlayer exciton, it has a very strong dependence on the exciton. Now, we only see the anti-crossing, say here on the top layer and not in the bottom layer. And I'd like you to take my word for it that this is an indication that we only have coherent hole tunneling. If we had coherent electron tunneling, we will also have anti-crossings on the bottom layer, or vice versa on the other side. Okay, so this is something we anticipated, that we expected actually, because of the large barrier for tunneling for electrons and much smaller barrier for holes through the HBM. So let's focus on these regions. Again, the structure now is what's happening here is the hybridization of these two excitons, whose energy we tuned by using the dipole. But what is nice here is that, or what is well, for us nice, is that we don't have just one interlayer exciton. We can see three of them. And the way to understand this is the fact that we have this moire potential, the superlattice potential, which actually results in different types of interlayer excitons, depending on where the electrons and holes sit. So this is a field that has emerged also about 2 years ago. People looked at interlayer excitons, not the hybrid excitons that I'm showing you. And there was theoretical work followed up by experiments, which showed that depending on where, what part of the superlattice the electron and holes sit, they have a different energy, and that results in these, depending on the twist angle, different excitonic resonances. And this is very prominent for interlayer excitons, but it is small compared to, for intralayer excitons, which is what we see, right? So basically, the fact that we see essentially a single intralayer exciton says that the moire effect is not important. Okay, so now I'm really running out of time. So what I would like to carry with you so far is that the spectroscopy has shown that there is the electron tunneling is vanishing the small. It's smaller than at least the exciton line width. There is a moire potential. So and this moire potential, the splitting of these excitons confirms the 24 nanometer sort of moire periodicity that we find from other experiments, and then that the intralayer excitons see a vanishing the small moire potential. Okay, so now Based on this, we expect the electronic states would be subject to a weak Moiré potential, and because they do not tunnel, they will have a preserved layer degree of freedom. That is, unlike the bilayer graphene example, whether the electrons are in top and bottom layer, this is still a good pseudospin type degree of freedom. Okay, so now let's look at the structure. Again, this is a nice animation that my student Clemens did. So this is, say, the bottom layer molybdenite. The big circles indicate the metal atoms. And then we put on top another molybdenite, and then we rotate the top layer. And then you can see that depending on where you are, you have different regions. So for example, in these ones that I circulated, the metal atom in the bottom layer overlaps spatially with the chalcogen atoms in the top layer. And then there are these other regions, what I will call MX, where the metal atom in the top layer overlaps with the chalcogen atoms in the other region. And then there are these parts which have a higher energy where the two metal atoms overlap. And you can see that, you know, if you just look at these 2 points, we essentially have a hexagonal lattice. But if you only look at what happens to the bottom layer, we have a triangular lattice. Okay, so now again, what the DFT calculations tell us is that the electrons at MX sites, so the metal atom of the top layer, has the lowest energy states for the top layer electrons. Converse is true for XM sites, so then the electrons in the bottom layer have lowest energy here. And given the periodicity, so to fill up all these sites, for example, the red ones, we need about 2 times 10 to the 11 electrons. Then we can fill up each site with 1 electron. Okay, and so this is something you have to take my word for it, but it's an easy calculation to show that the Coulomb interaction in this system is the largest energy scale, and it's followed by the nearest neighbor Coulomb interaction. So basically, on-site Coulomb interaction is dominant, and the nearest neighbor Coulomb interaction is still larger than the potential, the Moiré potential in the system. Okay, so now. So I want to apply this technique that you came up with to show you the charging diagram of this bilayer. So we have, depending on what top and back gate scans we use, the excitons can behave very, very different. And you see 3 different examples here. The idea now, again, is that for both bottom layer and top layer, we choose energies, and depending on at these excitonic energies, whether the reflection is low or high, we can determine the charging of that layer. And I'm speeding up a little bit here, and you can see that in this case, for example, for the top layer, we have this neutral region extended out into this top corner, and the converse is true for the bottom layer. Okay, so and this is again determined by looking at these excitonic reflection at that specific energies. Now, what is really interesting is that if you combine these two, we can determine the total charging energy diagram. So the back and top gate voltages for which the material is neutral, the bottom layer is n-doped, the top layer is n-doped, both of them are n-doped, and the very low density region here, which is on the order of 2 times 10 to the 11, you see a very rather unexpected feature that is coming up. Okay, so this now I rotated this charging diagram such that this vertical axis is the chemical potential axis. So this, if we change the voltages in a way, in accordance with each other, then we only change the electron density. Along this axis, we only change the electric field. Okay, so what is really remarkable, I think this is already apparent here, is that if we now look at this exciton energy for the top layer, what we see is that depending on the electric field, it basically, now I plot the derivative, so not just its energy, but how it changes. So you can see that here, the derivative is finite, is increasing, telling us that we dope the top layer. And then it becomes negative, saying that we actually, even though we're increasing the chemical potential, we're depleting the electrons from the top layer. Okay. Now, the opposite is true for negative electric field. So the zero of the electric field is here. This is -1 volt because of the asymmetry of the structure. Here, we first do not have any electrons in the top layer, and then we dope them into the top layer. And of course, the opposite is true for the bottom layer, such that when you superimpose the two, you see that depending on the electric field, you either put electrons into the top layer or bottom layer, but after a certain amount, which is 2 times 10 to the 11, filling the top layer stops, we start filling the bottom layer. Or for negative gate volt electric fields, the opposite is true. Okay, so this is already telling us that the electrons do not just continue to go in, and once a certain number is reached, that we cannot put any more electrons into the system, at least for low electric field values. Okay, and indeed that this is precisely the filling factor 1/2, which means 1 electron irrespective of its spin per Moiré site, and this is 2 electrons per lattice site, the superlattice site. Okay, so maybe I'll just show you this diagram. So this is now how the excitonic response, again, this is reflectivity, color-coded, changes as a function of electric field only. And what is really nice is that this is at nu equals 1/2. That is, the electron density is precisely at this level where the dashed lines are. And what you see is that here, the top layer exciton is the same as its sort of bare value. There is no attractive polaron, saying that there are no electrons in the top layer. And then at the 0 electric field, there is a jump. And now there's a blue shift of the top layer. And then we see that there is an attractive polaron resonance. So meaning that the electrons are now in the top layer. The opposite is true for the bottom layer. We start out seeing the attractive polaron, then it disappears, and then we see the resonance. And actually, if we do this gate voltage scan very carefully and with small steps, we see that this drop is extremely sharp. It actually takes place when we change the energy of the 2 layers, single particle energy, by 20 microelectron volts. And these experiments are carried out at 4 Kelvin, where KT is 400 microelectron volts. So it is clearly telling us that there is we are dealing with an incompressible state, that moving electrons one by one is just not feasible at this filling factor because of the interaction effects. And the way to understand it is this, that I told you that intersite interactions are strong. So let me actually go to this. So this is, for example, a scenario, say that we have unity filling of the top layer, the bottom layer is empty, and there is no tunnel coupling for electrons. So if we now try to move an electron from the top layer to the bottom layer, right? Say through the contacts, even though tunneling is not possible, we can actually sort of move electrons. So if that were to happen, you see that this nearest neighbor interactions are going to increase, or are going to forbid such a transition, because the top layer electrons only have the next nearest neighbor interactions. As soon as we move an electron to the bottom layer, because of the potential minima being in different sites, we're going to have to pay twice the V1, the nearest neighbor interaction. Okay, so in that sense, moving electrons one by one has this large potential energy barrier of 5 milli-electron volts or so. That's why it is forbidden at 4 Kelvin. But of course, the electrons can move all in one go from one layer to another, and that's why this transition at nu equals 1/2 that you see is so abrupt, because as soon as you change the electric field to a positive value, now it is energetically favorable for the electrons all to be in the bottom layer or top layer, depending on which configuration we're considering. Okay, so I wanted to tell you about the charge order, but given the time that I already took up 1 hour, I will just stop here and maybe just show you, tell you that presence of an electronic lattice, a Mott or a Wigner state, actually has its signatures in optical spectrum, because it basically creates a superlattice for excitons, and the excitons can scatter off these electrons and have new energy bands, excitonic energy bands now in this sort of mini Brillouin zone, and this is precisely what we use to monitor the emergence of charge order. Okay, thank you for your attention. I'll stop here.
Hocam, thank you so much. It was a great talk. Now maybe we can take some questions from the audience if there are any. So give me 1 second. Okay, over the YouTube, I don't see any questions. Ersan Hocam, do you have any questions? Okay.
Yes.
We are listening.
Can you hear me?
Yes, I can hear.
Can you hear me?
Yes, absolutely.
Thank you very much for your interesting talk. Of course, this is a very rich field. My question is related to exchange effects. You talk about this exciton-electron system together, or exciton-electron systems. There can be exchange of electrons, right? So between electron and the electron of the exciton, or electron and the electron of the boron, because of scatterings, and then it may change magnetic properties. Maybe can you comment on these issues? Did you study, or do you know about all these magnetic studies for these exchange effects?
Yeah, so basically, exchange plays a very important role in determining the binding energy of the trion, and which in turn determines the interactions between excitons and electrons, as I indicated that earlier in the talk. So basically, exchange plays an important role, and this is actually the reason why the only bound state of H- molecule, as well as the trion, is a singlet state, right? So basically, 2 electrons in 2 dimensions or 3 dimensions cannot bind to a hole if they have the same spin. So at that point, we see that the exchanges is playing a crucial role, because the symmetric wave function is the only way of the electrons, is the only way to have a finite binding energy. Now, this in turn has this result that excitons in a given valley can only be dressed effectively by the electrons in the K prime valley. Okay, so there is also some repulsive interaction with electrons in the same valley, but it is weaker than those effective repulsive interactions with the K prime valley, and there is no attractive interaction leading to attractive polaron formation. So this actually is very nicely visible here. So you can see that the attractive polaron for one polarization, meaning, let's say in this case, excitons in the K valley, sigma plus polarization, has this very nice attractive polaron resonance. And if you look at sigma minus, you see a very weak attractive polaron. And this actually is, we determined, is due to optically injected electrons with the wrong spin. So at 14 Tesla, if we turn down the light intensity, this is completely absent. All the electrons are in one valley, and then we see this attractive polaron only when the electrons and excitons are in different valleys. So in that sense, the exchange interaction that determines the nature of interactions is playing a crucial role. Related to this is the magnetic response. So if you look at the G factor of this exciton versus attractive polaron, they're very different. So the G factor of the repulsive polaron or exciton actually starts out at 4.3 and it goes through 0 and becomes negative. And that you can see that this resonance is lower in energy than this one, but because of this effective repulsive polaron formation, it blue shifts much faster than the exciton in sigma minus. For attractive polaron, the G factor is about 16 or so at its maximum. So it's again well below the usual expected values. And then finally, there is exchange playing a role in determining electron value occupancy. So value and spin are linked in this system because of large spin orbit interaction. And what we find is that the effective G factor of electrons can be, or holes can be as large as 30. So indicating that this is a strongly paramagnetic system, and the reason or the understanding for that is the exchange interactions favor occupancy of the same layer. I don't know if that answered your question, but these are the ways that I see in which exchange really comes into play.
Hocam çok teşekkürler.
Yes, mostly.
Thank you so much.
Okay.
So it was great to host you here, hocam.
Teşekkürler.
It was our pleasure. Maybe next time, in person, we can host you in the department.
Okay. I would love that.
That would be great for us because there are a lot of students who are very interested in your work in our university and in Turkey in general. So it would be great to host you here. So thank you so much.
Teşekkürler.
Çok teşekkürler hocam.